Okay, so let's get started. We're doing some examples. We were talking about integrals in 3D. Now, let's kind of kick today off with another example. Where we're going to find the volume of the region that we'll call D enclosed by the surface Z is equal to x squared plus 3y squared and Z is equal to 8 minus x squared minus y squared. So we have two surfaces here, and they kind of enclose some region collectively. So we need to kind of figure out what that region is, and then kind of move forward from there and figure out what the volume of this thing is going to be via triple integral. So the first thing we need to do is we can recall that the volume of an object is just the triple integral of 1 dv, where d is the region that, where the object is located. So we can use a triple integral with an integrand of 1 to calculate this volume. Okay, so step 1. We need to ask ourselves, where do these surfaces intersect? Right, where do we what region are we talking about here? So in order to figure out where these intersect, I can look at these two expressions and set them equal to one another. So we have that x squared plus 3y squared, which was equal to z, is also equal to 8 minus x squared minus y squared. So we can rearrange this a little bit. This is 2x squared plus 4y squared is equal to 8. Okay, so this expression details the curve that is the intersection of these two regions. So we can simplify this a little bit. We can get x squared plus 2y squared is equal to 4. So if this is where these things intersect, and notice here that both of these are functions of x and y, right? I have a z equals and a z equals. So if I kind of look at maybe a side view of what might be going on here, and now this isn't necessarily what these look like, but we might have a surface here. We're taking a side view. Maybe it goes up and down, in and out of the screen. Doesn't quite matter. But what we have is another curve that might do something like this, and it also might go in and out. But notice here that the view of where these intersect into the XY plane is one coherent shape here, right? So maybe for our random sketch, we might have some curve that is the intersection of these two surfaces, right? And they don't intersect anywhere else, right? So this top curve won't be able to project anything from further over, nor does this bottom curve project anything down onto the XY plane from further over. So their intersection, because these are functions, details the outer edge of the projection, right? So this is our shadow of this region here. We project all the intersections down. Okay, so if this is the thing that details the shadow that's cast onto the XY plane, so this means that our projection of D onto the XY plane is the region enclosed by x squared plus 2y squared is equal to 4. Or maybe we solve for y here. This is plus or minus the square root of 4 minus x squared over 2. Okay. So this is our projection. So step 2. Which is the upper / lower surface for the z bounds. So if we have some kind of z component right here, so maybe our surface looks like this, the question is which one of these is the top one and which one is the bottom one? Because our z coordinate or z bounds has to go from one to the other. So we need a lower bound and an upper bound. Well, what we can do is we can plug in any single point that exists in our projection, right? So basically what we're doing is if our projection is down here, the shadow that it casts, right, some kind of shadow domain, we can pick a single point and that xy coordinate will have a z component in both of these surfaces, and we can see which one is larger. And we know that they don't pass through each other again, right? There's only one curve of intersection for these two surfaces. So one's always going to be the upper and one's always going to be the lower as long as we're in the region of D. So we can just plug in some points. Notice that the origin is included in this. So at the origin, z is equal to 0 squared plus 3 times 0 squared is equal to 0. And then we also have that z is equal to 8 minus 0 squared minus 0 squared. Right, these were our two functions. We're plugging in x and y. This is equal to 8. So this one is our upper function, and this one is our lower function. Okay, so step 3. We need to figure out the y bounds, or we could do x bounds or y bounds dependent on how you want to look at the shadow. It is an ellipse. In this case, I'm going to look for, because I've already solved, y is equal to plus or minus the square root of 4 minus x squared over 2. I can use the upper, the plus, and the lower one, the minus, as my y bounds here. So the y bounds are from the projection that y is equal to plus or minus the square root of 4 minus x squared over 2. And then finally, we need the x bounds. The x bounds should be constants. Because it's the last bound that we're doing. So we're doing dz, dy, dx. So we have to look at the range of values that come from this ellipse that we've generated, right? The smallest and largest x values on this ellipse. The largest slash smallest x takes on the ellipse. This x squared plus 2y squared is equal to 4. So this happens when y is equal to 0, right? Because then we can have the largest x here, right? So if that's the case, when y is equal to 0, we have that x is equal to plus or minus 2, right? Because our ellipse perhaps looks something maybe like this. And the x, this is a terrible ellipse. Let me just actually draw a real ellipse. There we go. So when y is equal to 0, we have the edges here. So x is plus or minus 2. So step 5 is the volume is then we set it up. We have our triple integral of 1 dv, which we're doing dz, dy, dx. We said that z went from our lower function, which we found to be x squared plus 3y squared, to our upper function, which was 8 minus x squared minus y squared. Then these outer two talk about the projection. So we're doing the area integral. And we said that the y went from the bottom of the ellipse, which was negative square root of 4 minus x squared over 2 to the positive square root of 4 minus x squared over 2. And then finally, our x bounds were the range of these vertical traces that we were doing, which is -2 to +2. And that's the setup for the volume of this object. So let's go ahead and actually integrate this. Let's give ourselves a little bit more room here. So we have -2 to 2, and then negative square root of 4 minus x squared over 2, and then the positive 4 minus x squared over 2. Then we integrate with respect to z, and then we plug in our z bounds. So if we go ahead and do that, we have this 8 minus x squared minus y squared minus x squared plus 3y squared, which ends up giving us 8 minus 2 x squared minus 4 y squared dy dx. So -2 to 2. And then we can integrate with respect to y. So these are both constants with respect to y. So we have 8 minus 2x squared times y minus 4/3 y cubed, evaluated at y is equal to negative square root of 4 minus x squared over 2, and the positive 4 minus x squared over 2 dx. So we go ahead and plug those in. -2 to 2. I'm just going to simplify it a little bit ahead of time. So remember, we're plugging in this and then subtracting this, but we have this negative here, right? So wherever we plug this in and it remains negative, we're actually subtracting that. So we actually, for this first term, we plug this in, and we have an 8 minus 2x squared times this quantity. But then we subtract that same thing, but with a negative. So it really is adding that. So here we get an 8. I'm going to actually pull out. No, I'm actually going to write it like this first. 2 times 8 minus 2x squared times the quantity of the square root of 4 minus x squared over 2 minus, and then we double up again. So we have 8 over 3 of the quantity 4 minus x squared over 2 to the 3/2 dx. So now what I'm going to do is I look at this term here. This is a 4, or sorry, this is an 8 minus 2x squared. But if I pulled out a 2 and made this 4 minus x squared, and maybe I even pull out another 2, so I would ultimately pull out 4, I could write this as 4 minus x squared over 2, right? Well, this is this term right here. So what I could do is simplify this as 8 times 4 minus x squared over 2 to the 3/2 power. So this is me rewriting this first term minus 8/3, and then I'm going to just keep the second term without changing anything. And now I have a similar term here, this 4 minus x squared over 2 to the 3/2 power. So this is the integral from -2 to 2 of 4 root 2 over 3 4 minus x squared to the 3/2 power dx. So I pulled out the 1 over 2 from both of these terms, and now I just have some constant value out in front, and then I have this 4 minus x squared to the 3/2 power. I'm not going to dive too deep into doing this integral, but this is a trig substitution. So we can say we let x equal 2 times sine of u, and then dx is equal to 2 cosine u du. So this integral then becomes negative pi over 2 to pi over 2 of 4 times root 2 over 3, 4 minus 4 sine squared of u to the 3/2 power times 2 cosine of u du. So when you do that substitution, notice here we can take advantage of the fact that sine squared plus cosine squared is equal to 1. So this is, you can factor out a 4, and then this is 1 minus sine squared, which in fact then is just cosine squared. Then we take the square root and then cube it. So this ultimately becomes, we pull out the 4, it gets hit by this 3/2 power, but then we have a cosine cubed times a cosine here, and then you do a bunch of double angle formulas. That's kind of lengthy, but what you ultimately get is 8 pi over root 2. The big takeaway from this is setting up this triple integral, right? Now, at the end of the day, once we do this integration, perhaps we have to revisit techniques that we've learned in the past, like trig substitution or integration by parts. But I kind of want to focus on setting up these triple integrals, because this is the Calc 3 concept. Okay. So with that, let's do one more example. And then we'll start talking about some applications. So we're going to write down 6 different integrals finding the volume of the object bounded by y is equal to 0, x is equal to 2, x is equal to 0, z is equal to 0, and y plus z is equal to 1. Okay, so what does this thing look like? So let's first do a rough sketch of what's going on here. So here we have our x, y, and z axis. So we've got x, y, and z. We know x is equal to 0, which is the zy plane is a bound. Then we also have that x is equal to 2. So we'll kind of mark here that x is equal to 2. Right? So then we have the x equals 2 plane. Then we have the z equals 0 plane, which is the xy plane, so the bottom here. Then we have y is equal to 0, meaning the zx plane. And then we have this plane, this y plus z is equal to 1. So this actually creates, let me actually do straight lines here. Kind of like this prism. Right, because notice there's no x in this plane equation. So it looks like it doesn't really morph in the x direction. So it has the same slope no matter which x value we take. Right, so it looks like this little prism. So this is a pretty basic object, but let's see if we can write this in 6 different ways. Okay, so let's kind of first decide on the orders that we're going to be doing. So in Cartesian coordinates, we have that we can write this as x, then y, and then z. We can also do y, then x, then z. We can also do z, and then x, and then y. We could also do x, and then z, and then y. Could also do y, and then z, and then x. And finally, we could do z, and then y, and then x. Okay, so this is 6 different ways. So let's see if we can write out the integrals that would compute the volume of this object, specifically in the integration order x, y, z, and then so on, y, x, z, and then y, and z, x, y, and going on and on and on. Okay, so let's do A. So we need to do a triple integral with 1 as our integrand, and we do dx, dy, dz. So let's look back at our object here. X goes from this edge all the way over to this edge, right? So the functions that detail this are x equals 0 and x equals 2. Okay, perfect. 0 to 2. Y, so we now have to look at the projection of this object onto the latter plane. So if we get rid of x, we do x first, we're looking at the yz plane, right? So we project the shadow of this object onto the YZ plane. Well, because it's uniform in the X direction, it's always going to look just like this triangle right here in the YZ plane. So let's just do a quick sketch of what this looks like. And we won't do this for all of them because you'll get the idea. In the YZ plane, our projection just looks like that triangle. And we can actually find out these points. It ends up being 1 and 1. We just look at this equation. So when y is equal to 0, x or z is equal to 1. And when z is equal to 0, y is equal to 1. So this becomes the equation we can write as y is equal to 1 minus z. So our projection goes from y equals 0 up to that line. So 0 to 1 minus z. And then finally, z is the range of all of these traces. Sorry, this is the yz. Should write that in. Right, so we're going from 0 to this line. And then we're going in the z direction. Shouldn't it be z is equal to 1 minus y? It's also that. This is also, if you just rearrange this, this is also z is equal to 1 minus y. So we were doing traces in the y direction here. And then we need to find out the range of these traces in the z direction because we're doing z last. So this goes from 0 all the way up to z equals 1. So that's our first way of how we write this volume in the specific ordering. So then for B, maybe I should give myself some room for the upper bounds. We're doing dy, dx, dz. Okay, so now we look back at our prism here. Y goes from here all the way out to the plane. So that means we go from 0 to that plane equation, but that plane equation was just y plus z is equal to 1. So we can say that this is 1 minus z, solving for y. Then our x bounds, the trace in this direction is going to be on the xz plane. So on the xz plane, we have just this rectangle, right? And x goes from 0 to 2, and z goes from 0 to 1. So this is how we write this volume in this dy, dx, dz. So now for C, we're doing dz, dx, dy. Okay. Now x, sorry, we're doing z first. Since we're doing z first, let me get rid of these arrows because now we're going from the bottom up to this plane. So the plane equation we could rewrite as z is equal to 1 minus y. So we go from z equals 0 to z equals 1 minus y. And then we need to look at the projection on the xy plane. So the projection on the xy plane is this rectangle. The x bounds go from 0 to 2. And the y bounds go from 0 to 1. Okay, so D, which was x, z, y. So now we're doing the dx again first. And we saw, just like A here, that the function x equals 0 and x equals 2 are the bounds for this. So we go from 0 to 2. And then we look at the projection on the zy plane, which again is this triangle. But now instead of doing dy dz, we're doing dz dy. In this case, z is going from z equals 0 up to this line. And this is when we'll use z is equal to 1 minus y. So this goes from 0 to that line, 1 minus y. And then dy goes from 0 to 1. Right? That's the range of those traces. So for our triangle here, we're going from 0 to 1. Okay. E was dy, dz, dx. So we've done a dy first, right? The y in this case, well, I have to erase these again. Our y is going from here out to the plane. So we go from 0 to y is equal to 1 minus c. Then we look at the zx plane. Well, zx is this rectangle here. So we can easily write the bounds for that rectangle. Z goes from 0 to 1. And x goes from 0 to 2. And then finally, we have f, which is in the order dz, dy, dx. And we've done a dz before. So z goes from the base up to this plane equation. So something like that again. So we can solve for that plane in terms of z. So we get 0 to z equals 1 minus y. Then we project to the yx plane. The yx plane is this bottom rectangle, and that's pretty easy for us to find the bounds for. In the y direction, this goes from 0 to 1. And in the x direction, this goes from 0 to 2. Okay, that's 6 different ways for us to write this volume. Right, so maybe you go back and you try to replicate these without seeing the solutions. Get some practice with rewriting volumes in terms of different orderings of dx, dy, and dz. Okay, now with that, let's talk about applications. So the first thing we're going to talk about is average value. So the average value of a function that we'll call capital F of x, y, and z over a domain D in space is the triple integral of D over F dV divided by the triple integral of D dV. Okay, so what's happening here? Think of how you would normally calculate an average. Maybe you're looking at, an average of homework scores or something, right? You add up all of the scores and then you divide by how many that there were, right? So maybe there was 5 assignments and you had 5 different scores. You add up all those scores and then you divide by 5, give you the average value. This is exactly the same thing. Remember, think of integrals as sums. So what I'm doing is I'm adding up all of the points in D of F. So at x, y, z, I add a point. At another x, y, and z, I add another point, and I continuously add all of the points in D of the function f, right? And then I divide by the number of points, which is the volume of that object, right? So we can also say that this denominator here so the volume of D is equal to the triple integral over D dV. So maybe if this was like a really easy question, you've got where D is a cube, the bottom of this could be calculated just using length times height times width. But the top, this numerator here, is not going to be as easy because our integrand doesn't necessarily is uniform in space. But this is exactly what's happening here. We're adding up all of the scores of F divided by the number of them, right? Which ends up being this volume. All right, so let's look at an example. We're going to find the average of x times y times z over some domain D that is the points x, y, and z such that x is bounded between 0 and 2, y is bounded between 0 and 2, and z is bounded between 0 and 2. So it looks like we have that our domain describes a cube. So the first thing we can do is say that the volume is just a cube of length and width and height of 2. So our volume is just 8. Great, that's our denominator. We didn't even have to do a triple integral. But for the numerator, we're going to have to. So next, we need to calculate the triple integral over d of this function f that was x times y times z. So because we're just over some cube, the bounds are pretty easy. This is 0 to 2, 0 to 2, and 0 to 2 of the function x times y times z. And I'm going to choose to just do dz, dy, dx. So we need to do this integral now. This is equal to our double integral, both from 0 to 2, of x times y times, z squared over 2, where z is equal to 0 and z is equal to 2, dy dx, or this is our same two outer integrals, 0 to 2, 0 to 2, of 2 times x times y dy dx. Or the single integral from 0 to 2 of 2 times x. We do our y integration now. We get a y squared over 2. Y is equal to 0. Y is equal to 2 dx. This just gives us the integral from 0 to 2 of 4 times x dx. And this will give us 2x squared, x equals 0, and x equals 2, or we get 8. So the average is then 8 over the volume, which was also 8, which is equal to 1. Okay, if the average of x, y, z over this cube is equal to 1, does that make sense? Let's kind of think about this. So x, y, z doesn't necessarily need to be positive. Well, it is in the interval from 0 to 2, 0 to 2, 0 to 2. Okay, so you convinced me that this product at least is non-negative, right? So when it's really close to the origin, it's really small. right? And it linearly increases with x, linearly increases with y, linearly increases with z, right? And if you're all the way at 2, 2, 2, the value is 8, right? 2 times 2 times 2, right? So in one corner, I've got 0. In the other corner, I got 8. And it linearly increases in the x direction, in the y direction, and the z direction. So it makes sense that the average should be 1. So if you look at each one of those little cubes that you can like subdivide into, you can get that, one value has, like an eighth, or sorry, 1 or 0 all the way up through 8. So this average makes sense, right? If you add it up, just the values that go from 0 to 8, right? And you had 8 of them, the average would certainly be 1, but now you're doing this in higher dimensions, so it works out that this average is in fact 1 here. Okay. So now let's talk about mass. Now we talked about mass and moments in using double integrals. Now let's talk about doing mass with 3 integrals. So if we have a density of x times y times z, in units of mass per unit volume, we can derive the total mass as the triple integral over E, where E is the region that describes the volume that you're interested in, of the density dV. Right, so very similar to before, where we had the mass of maybe a really thin plate, where you could kind of break these up into the mass of each of these small rectangles and then add those all up. The same thing goes here, except now we're going to be talking about volumes of really small cubes that you end up summing over, right? So the mass is the triple integral over E of the density function, right? And this will give us ultimately the total mass of this object. So now for moments. So before we define these moments about an axis. So when we're in R3, we have to do this via planes. So we have to define all of our moments across certain planes. So we have a moment that goes across the YZ plane. So we have the triple integral over the region E. Remember, it's always the distance to that axis, or in this case, a plane, and the distance from the YZ plane is equal to x times our density dV. We'll also have a moment across the XZ plane, which is the triple integral over E of y, the density, times dV. And we'll also have a moment across the XY plane, which is the triple integral over the region E, z times our density function. Let's take our break in just a second. I'm gonna finish this up and then we'll take our break. Sorry, we went a little bit over. So the center of mass is then x bar, y bar, z bar where each of these we can write as x bar is the moment across the yz plane divided by mass. Y bar is the moment across the xz plane divided by mass. And then z bar is the moment across the x y plane divided by the total mass. And then we're just going to define one last thing, and we'll take our break. If the density is constant, the center of mass, COM, is called the centroid. Of the volume E. Just a special name that's given to objects that have constant density. Okay, so why don't we take our 5-minute break? We'll pick up again at 1:47. Okay, so let's pick up again. That was our first moment. So let's talk about our second moment, or the moments of inertia in using triple integrals. So in this case, because these are talking about rotation, these are about axes rather than around planes. So we define the moment of inertia across the x-axis as the triple integral over the region E from the distance from that x-axis, which is y squared plus z squared times our density dv. We have about the y-axis, which is our triple integral, and the distance from the y-axis is x squared plus z squared. And then we have times our density dv. And then we have our moment of inertia about the z-axis. Our integrand will be an x squared plus a y squared. Times our density, dv. Okay, so now let's look at an example. we're going to find the moments of inertia of the solid of constant density rho, defined by D is equal to the set of all points x, y, and z such that we have x bounded by negative a over 2 to a over 2. We have y bounded by negative b over 2 to b over 2. And then z is bounded by negative c over 2 to c over 2. So it looks like we've got a rectangular prism with length a, height or width b, and height c centered at the origin. We know that it has constant density, which is pretty nice. So let's go ahead and try to find all of these moments of inertia. So my first one will be about the x-axis. We have c over 2, negative c over 2, b over 2 to negative b over 2, and a over 2 to a over 2. Y squared plus z squared times rho dx, dy, dz. Okay. So there's a few things we can take advantage of that make our jobs a little bit easier. First things first, I'm not going to calculate Iy or Iz because I realize that they're all going to give me the same thing. Well, they're not all going to, sorry, I misspoke. They're not all going to give us the same thing, but what they all are doing is that they have symmetry about them, right? Y squared plus z squared is even. Oh, this should be a negative. Thank you. To a over 2, correct. So the integrand is even for all of them, right? I have a y squared plus a z squared, or I have an x squared plus a y squared, or an x squared plus a z squared. They're all even functions, right? So that means I can save a little bit of work by saying that, for instance, this integral is 2 times the integral from 0 to c over 2 2 times the integral from 0 to b over 2, and 2 times the integral of 0 to a over 2 of y squared plus z squared times my constant density rho dx, dy, dz. And we could brute force this, but this is nice taking advantage of the symmetry. This is equal to, what is my thought process behind that step? So the fact that this is an even integral, meaning that if I reflect it across the y-axis, it's the same. Where I reflect it across the z-axis, it's the same. Or I reflect it across the x-axis, it's the same. So instead of going from negative c over 2 to c over 2, I'm just going to take double from 0 to c over 2. then likewise in the y direction, since this is the same thing across y equals 0, I'm going to go from 0 to b over 2 and double that. And the same thing in the x direction. You can brute force this. This is fine. You can do this integral out, but I like having zeros here. So this is in total 8, and I can pull out this constant rho now. 0 to c over 2, 0 to b over 2. And I'll actually go ahead and do the x integral out because there's no x's in here. So you'll just multiply this by an x and then plug in 0 and a over 2. This will give me a over 2 times y squared plus z squared dy dz. So let's keep doing this double integral now. I can pull out this a over 2, and I get a 4a times rho, the integral from 0 to c over 2, the quantity y cubed over 3 plus z squared times y equals 0 and y equals b over 2 dz. 4a times rho, 0 to c over 2. This is the quantity b cubed over 24 plus z squared times b over 2 dz. Can keep doing this out. This is 4a times rho. Now we're doing this integral. This is b cubed over 24 times z plus z cubed times b over 6, z equals 0, and z equals c over 2. This is 4a times rho, b cubed times c over 48 plus c cubed times b over 48. Or I can write this a little bit nicer, and you kind of actually see the pattern here. I get a, b, c over 12 times the quantity b squared plus c squared times rho. Okay, so that was for Ix, and I said that we're not going to be doing Iy or Iz, because what we could do is notice again the symmetry that's really happening here, right? So notice the form that I have for ABC over 12 times b squared plus c squared. Well, b and c were the variables that linked us to y and z, and we started with a y squared plus z squared. If you imagine that we went ahead and we replaced maybe this y with an x, right? Then we're doing Iy. Well, what we would do is reorganize the integration so that we would do dy first, and then we would go from 0 to b over 2, and then we get instead of this step here where we get a over 2, we get a b over 2. And then we would likewise do almost the same exact integral. In fact, if you do a substitution, these are all the same integrals, just with different parameters a, b, and c. So it turns out that Iy is equal to a, b, c over 12 a squared plus c squared times rho, and iz is equal to abc over 12 of a squared plus b squared times rho. And again, you can do these brute force, but taking advantage of the symmetry of this is really nice. Just think about what it means if I have this rectangle, right? You can even think about a cube, right? And you have axes of rotation. You can imagine that they probably have very similar forms, right? So we can just kind of logic our way through this step here. You can also just do substitutions and get back to this original integral with just slightly different bounds that result in the differences, what's inside these parentheses. Okay, so let's do one last example for this section. Let's find the center of mass of a solid of constant density rho bounded below by the disk x squared plus y squared is less than or equal to 4 in the plane z equals 0 and above by the paraboloid z is equal to 4 minus x squared minus y squared. Okay, so let's kind of sketch out what's going on here. So we draw our x, y, and z. We have the paraboloid z is equal to 4 minus x squared minus y squared. So we know it opens up in the z direction. And it's going to take a maximum of 4 at the origin, and then it's going to kind of descend from there. So we're at the origin, and then we kind of open up like a parabola, like this. And then eventually it's going to hit the xy plane, or the z equals 0 plane, and it's bounded below by some disk. So in fact, if you plug in z is equal to 0, you get x squared plus y squared is equal to 4, right? Which is the outer perimeter of this disk. But we also are including everything in here, everything inside this face. So we create this volume here. Maybe it looks kind of like a bullet. I'm going to call this region on the z equals 0 plane R. And this is z is equal to 4 minus x squared minus y squared. Okay. So again, let's put our engineering hats on and see if we can save ourselves from some work. So this is constant density, right? So if I look at this object across the YZ plane, it's the same on either side, which means the mass should be the same on either side, right? If the density is uniform, which means that the center of mass in that direction should be y is equal to 0, right? Same thing goes with the x direction. If you look at across this axis, right, it's still symmetric across either side of that plane, right? Same amount of mass on either side. So using symmetry and the fact that rho is constant, so we can argue symmetry. Which means that x bar and y bar are both equal to 0. The only thing that we can't convince ourselves is the z bar. So we're actually going to do the integral for this. So to find z bar, we first have to find the moment and the mass. So let's start with the mass. The mass of this is this triple integral, but I'm going to write it in this way, of the density rho, which is just going to be this constant, dz dA over this region R. And our z-bound goes from 0 to 4 minus x squared minus y squared. Right? The projection of this volume to the xy plane is this circle, right? It's the circle that's defined by x squared plus y squared is equal to 4. Okay, so let's draw a little plot here. The projection of this object is just this circle with radius 2. Right? This is x squared plus y squared is equal to 4. So the reason that I wrote it instead of using my Cartesian coordinates here for this area integral is I can calculate this z integral here perfectly fine, but then I have to do the area integral of the projection. Well, I don't want to use Cartesian coordinates. This is a circle, so I'm going to use polar coordinates. So let's go ahead and first do this z integral here. This is equal to our double integral over r of 4 minus x squared minus y squared times our rho dA. So I can change this into polar coordinates now. This is equal to my polar integral from 0 to 2 pi, 0 to 2, rho times 4 minus x squared minus y squared, which I can rewrite as r squared. We have our dr d theta, but remember for polar coordinates, we can't forget that we have this extra r in here. So now I've translated this into my polar coordinates. So let's go ahead and do it in polar coordinates. So we get this is equal to 0 to 2 pi rho of, so there's an r here, so we get a 2r squared minus r to the 4th over 4, r equals 0 and r equals 2 d theta. This comes out to 0 to 2 pi 4 times rho d theta, which ends up giving us 8 pi rho. Okay, so that's our mass. So now we need to calculate our moment. Our moment across the xy plane, again, I'm going to write it as this double integral with this third integral inside, which was 0 to 4 minus x squared minus y squared. This time we have the integrand being z times rho dz. And then we have our area integral out here over the region R again. Well, I can do the z integral. So this is the double integral over R. Then I have 4 minus x squared minus y squared rho over 2. Oh, and this should be squared here. Yep. dA. Okay, so now this is the double integral that I need to compute. Again, we could do this in Cartesian, but it looks like the region R is much simpler to do in polar coordinates. So I'm going to go ahead and write this in polar coordinates. I'm going to bring out this rho over 2. So rho over 2, the integral from 0 to 2 pi, the integral from 0 to 2. And then I have 4 minus r squared squared times r dr d theta. Okay, so we could do this out. We could FOIL all of this, but that's a lot. I'm actually going to do a u substitution here, where we do a u sub for this quantity. You could just FOIL it out. That's also fine. At the end of the day, you still get a rho over 2, an integral from 0 to 2 pi, and then a -1 over 6, 4 minus r squared cubed from r equals 0 to r equals 2 d theta. This gives us a 16 rho over 3, the integral from 0 to 2 pi d theta, or 32 pi times rho over 3. And that's going to help us find the z bar. So the center of mass is then x bar, y bar, z bar, which is equal to 0, 0, the moment about the xy plane, and the mass, which is going to give us 0, 0, and 4 thirds. Okay, so we just saw a glimpse into what we're actually going to be talking about in the next section, 12.6. So what do I mean by that? In 12.6, we're going to start talking about different coordinate systems in R3. Instead of Cartesian, we're going to first talk about cylindrical coordinates. And basically, this is exactly what we've done for this problem, but we're going to go more in depth with it in the next section. What we've done is we've kept z the same, but the projection onto our xy plane we considered to be polar coordinates. So we've kind of been foreshadowing this for a while, right? We had our triple integral. This is perfectly fine. This is a triple integral. We had our z, and then the projection that it cast was something easily described by polar coordinates. So let's jump to a new page, and we're just briefly going to get started on this next section, 12.6. Which is triple integrals in cylindrical coordinates. So the first thing we're going to do is extend our concept of polar coordinates to use z. So what we do is we let x equal some radius times cosine of theta. We have y be r times sine of theta. And then we have that z is equal to z. Right? So these first two are what we've typically used for polar coordinates. But now the elevation, or this thing in the z direction, is just the same as its Cartesian counterpart. It's just equal to z. This kind of extends the idea of polar coordinates into R3. So let's kind of look at a sketch of what this polar coordinates is kind of doing here. So we have our typical x, y, and z. But now say I have a point here that is point P, and the ordered triplet will be R, theta, Z. So what I'll do first is I cast a shadow down onto the XY plane. And then I have a line that goes from the origin in the XY plane out to that shadow point. So here I have the point R, theta, 0. And here, if this is the x-axis and this is the y-axis, then theta is the angle from the x-axis to this line. And the length here is r. And the length here is z. So this is how I define a point in cylindrical coordinates, is I measure the good old-fashioned polar coordinates in the xy plane, and then I move up a distance in the z direction. Okay, so before I really kind of solidify that idea, cylindrical coordinates doesn't necessarily need to be defined where z is equal to z. It could be that x is equal to x and that we have trig functions in the polar coordinates in y and z. Or we could say that y is equal to y, and then we can have the polar coordinate conversion for x and z instead. So cylindrical coordinates just means that two of the Cartesian variables are considered polar coordinates and the third one is equivalent. Most of the time you see that, like in your book, it's that polar coordinates are in x and y, and then z is the equivalent for the Cartesian coordinate system. But we could always rotate this to include polar coordinates for any of the other pairings. Okay, so how do we convert back from rectangular to cylindrical? Well, we could say that r squared is equal to x squared plus y squared in this case, we also can say that tangent of theta is y over x, and z, of course, is still equal to z in the example that we have up here. So some things that we're definitely going to have to be able to do is convert surfaces in Cartesian coordinates into their cylindrical coordinate counterpart. So let's just do a quick example. Where we have that z is equal to r. Let's define what this thing looks like. So what I'll do is I'll actually start to draw out something in R2. But what I'll do is write this as the xy plane, and I'll write this as the z-axis. So you can think of the xy plane as the r direction as well. So if I have that z is equal to r, then this is just a linear expression so I have just two lines that go like this, because I have to think about what happens when I go to R3, and this is still a radius, right? And then this creates a cone. Where the elevation z is determined by the length of r. So these are equivalent. So just looking at this, this is z is equal to r, you should think about this cone. But we should also, what we could do is that z squared is certainly equal to r squared, right? If I just square both sides. But r squared is equal to x squared plus y squared, which from way back when we learned was a circular cone. Okay, so with that, why don't we stop there? And tomorrow we're going to pick up more with cylindrical coordinates and triple integrals inside cylindrical coordinates.